Temperature differences between water, heated water cooling, and air temperature. So here's the data. Time, it's the explanatory variable, or the x variable, or whatever. And then here's the consequential variable. And you can see right away this is going to be exponential. Look at the rate of change here. Difference between these two numbers here. This is x changes by 10. 10 minutes go by, and the temperature goes from 68 to 36. 10 minutes go by, and then it goes down by 16. So that's 32 degrees it went down. Then it goes 16, 10, 4, and then 2. Clearly exponential, almost exactly powers of 2. So we know that we're going to re-express this with a log, but they want us to make a scatter plot. First, you put in the data, and second, and y equals, make sure it's turned on. You got L1 and L2, and then a zoom 9, and you can see it's exponential. All the data values are positive, which means you can re-express with logs. Remember, you can't take the log of a negative number. So, and like the exponential decay, you're coming from some theoretical infinite location up here somewhere, and then coming down to a horizontal asymptote on the x-axis. That's the the exponential function model. All right, so we go to stat and going into edit, and we're going over to L3, and we'll take the log of L2. And just make sure we did the right thing. Well, you can check it. 10 raised to the power of second 3. Okay. And you can see we got L2 back again. So we know that L3 really is the exponent that 10 is raised to in order to get the numbers in column L2. All right. And so now let's do a scatter plot on L1 and L3. Very straight. There's a bit of a bend, but we'll try. It's certainly worth trying a linear regression on. Turn on diagnostic. Don't forget doing an L1 and L3. Here's our equation. So let's look at the residuals. Okay. All right. Well, it's not exactly a curve. But given that we only got, again, you hear me going over and over again with this, 6 points is not very much. It doesn't look like a parabola, that's for sure. And it looks a heck of a lot better than the residuals we would have with the original scatter plot if we had to run linear regression on that. That clearly would look like a parabola. This does not. It doesn't look very random. It certainly goes up at the ends and comes down in the middle. But it doesn't have a parabolic shape. It looks irregular. Let's put it that way. It does not have, it has an irregular shape. Okay? Anyway, for want of a better term, it's better than what the residuals would look like. In fact, just for the sake of, well, let me finish this and you could go back. I'll tell you what, if you're not convinced, go back and run linear regression on L1 and L2 and look at the residuals. I guarantee you they will look like a parabola. Okay? Now this does not. So we're going to go with this. Now down here I took a picture. I didn't bother filling in these boxes. You can do that. There's only a few dots, so it's not hard to do. So here's the two scatter plots. Scatter plot that would go in here and the scatter plot that would go in here. Here's a picture of the residuals. Now let's go back to the problem. Okay, so we got our scatter plots. Let's see. So write the equation of the line. So here's our here's A and B, or B sub 0 and B sub 1. So 2.057 minus 0.0251, okay, times minutes equals the log of the estimated difference between the temperature, air temperature, and the water temperature. Okay, so we have our model. Again, because I don't like the rounding when we're using re-expression, because we're using this equation to calculate an exponent, not the actual number itself. And since exponents, the difference in exponents makes such a drastic difference in the product when 10 is raised to that exponent, I'm going to go to y equals, and I'm going to put my variable in. I'm going to go to vars, and then 5 for statistics, arrow over to EQ, and put the equation in. And then I'm going to go to 10, and up arrow. So I'm going to raise 10 to the power of y1, because y1 is the log. And I'm going to go to vars and y vars. Okay. And so now I can use the table. Okay, so use the equation to predict the difference after 45 minutes. Okay, there's a whole lot of different ways we could do this. Now, the units is minute. The units is whatever. Now, let's go to the table. Now, this table is not set up by the way I had it. So here's the table. So here's 45 minutes. So the temperature, the exponent after 45 minutes is 0.92726, and so the actual temperature difference would be 8.4579 degrees. Okay. Now, what's the time at 0 minutes? If you want, we can go to the second and then window table set. Oops, second and window. And let's make it, we can set it to ask. If you set it to ask, don't forget to set it back. Well, I don't know, it's up to you. Maybe you will always want to have it that way. Alright, so let's put in 0 minutes. Okay. So that's that 0 minutes represents the temperature difference at the beginning of the experiment. And we can put in 45 like we did before to answer both our questions. And so after 45 minutes, the temperature difference is only 8.45 degrees. And that, I believe, answers all the questions. Down here is some math that shows you how you convert from the log expression into the exponential, and from the log on both sides into the power. Anyway, all right, that's it.